Great. Well, thank you everyone for coming. Well, as Mike alluded to, talk will mostly be focusing on the 2018 Anchorage earthquake. Some of the science that came from it. I'll avoid some of the engineering repercussions from this earthquake because I'm not an engineer, and I don't even pretend to be one on TV. So I'm going to just avoid all that as much as I can. But hopefully some interesting things that came from it scientifically and some steps to the future that we can look forward to as a state from this earthquake.
Can we turn down the lights? Well, we can turn down the lights a little bit.
All right, well, as Fritz is doing that, I'll keep going. To start with, talk a little bit about the Earthquake Center itself. We're based at the Geophysical Institute at UAF. Between all of us, we're a group of about 20 people, faculty and staff. We sort of range the gamut. There's scientists, engineers, data analysts, folks who specialize in IT, educators, pretty much the whole range. Although truth be told, most of us wear various multiples of those hats day in, day out, depending on what the needs are at the given time. One of the main things we do is we're trying to increase Alaska's resilience to earthquakes through a variety of things, public engagement like lectures such as this, and in particular, we can't do our core mission without earthquake monitoring of the state. So a brief little overview. We don't need to worry about symbols or anything like that, but all of the red points on the map of Alaska are seismic stations that are owned and operated by the Alaska Earthquake Center. We're currently at about around a little over 200 of them, sending data back to us in Fairbanks 24/7 continuously. And within that, we partner with anybody who's willing to operate a high-grade seismometer within the state. We have numerous partners such as the National Tsunami Warning Center, the Alaska Volcano Observatory, the National Science Foundation, to supplement the network. And they all have different missions. They deploy seismometers for different reasons, but it doesn't matter to us. They all help for us to locate earthquakes. And so I often, with operating 250 sites or so, that involves a large component of field. We have dedicated people day in, day out, or at least in the summers, who are gone most of the time specifically to service these sites and do routine maintenance or fix problems that have cropped up. And when they come back to the lab, they always like to show us beautiful pictures like this, showing some of these crazy sites that they're at, often on vistas on hilltops, overlooking just gorgeous panoramas, things like that, and come back and go, oh man, I may have chosen wrong being more of an office jockey. That being said, for every one picture like this, you get a dozen that look like this, or like this, or like this, reinforcing the fact that operating remote field sites in Alaska is hard. This is a really tough environment for things to function in and function year-round. So then I turn around and go, actually, maybe life isn't so bad all the time. All that data, comes into our lab, and one of our primary goals is to report on all the earthquake activity within the state of Alaska. And so no matter if you watch for earthquake information in the state, no matter how you get that information, whether it's from apps on your phone, the USGS webpage, if you visit our webpage, it doesn't matter. All that information originated in some form or another from us, and we push it out to all our various partners who then distribute it to have a wider range. Given that it's also 2020, we also have a presence on social media, on Twitter and Facebook, that helps us directly engage with the public as well and answer questions that they may have and things like that regarding particular earthquakes, in particular ones that people may have felt. So at the end of the day, we come up with we produce catalogs, we report on a whole bunch of earthquakes. This is a 2019 seismicity in the state. Every one of those dots is an earthquake. There was a little over 50,000 last year. It's a huge number, but the reality is, as Mike alluded to, that most of these were quite small. Nobody felt them. They have no societal impacts whatsoever. And so in the grand scheme of things, most of that is just day in, day out routine. It's something we do, we are trained, our systems are working on it, but it doesn't matter to the general public. That being said, there are certain days, like November 30th at about 8:30, where all of that changes. And so here I've got a little movie. I see how good the sound is for it. So this is a video from a classroom in Anchorage. They're recording remotely at the time. So that's basically what it was like, at least the initial main shock for these students. I love that video in particular. The kids are a perfect example of what you should do right after an earthquake. That is just, you couldn't put a better promotional material for how you should react when you first notice an earthquake coming. And then of course, you realize that they're actually kids. The first question they ask is, does that mean we get to go home for the day? Yeah, and most of them did. So, some basic information about that earthquake is magnitude 7.1. We'll talk about that a little more. It's 29 miles deep. It's about 8:30 in the morning. The maximum intensity, which is a very qualitative measure. It doesn't mean anything. There's no number you can assign to that. But it's a rough estimate of how the people would perceive the shaking. And that was rated on a scale called the modified Mercalli scale of an 8, which is severe shaking, although buildings that were designed to withstand seismic hazards are probably going to be fine with minimal damage. Although, key point, there's considerable damage in poorly built structures. In this case, Anchorage being a fairly modern city, there were very few poorly built buildings, but in other countries such as Turkey, Iran, China, places like that, an earthquake of this size, this close to population, could have been utterly devastating. It has a maximum PGA, peak ground accelerations, recorded at the surface of about 40 to 50% G. 1G being the acceleration of gravity. So if you jump in the air, you're basically experiencing 1% or 1G. So about half of that is the strong shake, which is actually a really strong amount. And perhaps even more noticeable from that was that peak ground accelerations of 25% G, which is still very strong shaking, were experienced over 3,000 square miles, which encompasses a huge portion of the population of the state. Anywhere that's, well, the colors are a little washed out there, but the oranges and the reds were all areas that experienced shaking of at least that strong. So this had a huge, this was widely felt. I felt it in Fairbanks. I'm sure many of you may have as well. We all have earthquake stories about that up here, although ours most likely pale in comparison to anybody who was down south that day. An earthquake of this size, you would expect aftershocks, and that's indeed what happened. Each one of these lines, these yellow lines, is data from one seismic station somewhere in south central Alaska. And you see, normally, on a normal day, these would be flat, just straight lines. Maybe there'd be one or two small little earthquakes showing up in there, but you wouldn't see all that much. In this case, over 40 minutes, it was just nothing but earthquakes right after the main shock, over and over and over and over again. And this was pretty typical. This is about what you would expect from an aftershock sequence from an earthquake like this. In the end, there were 17 aftershocks greater than magnitude 4 within the first 72 hours. And looking at the grand scheme of things, this is up until now because the aftershock sequence is still ongoing. There have been 6 greater than 5, almost 50 greater than 4, and almost 400 greater than magnitude 3. And that's about the level where people would feel them. So probably about 400 aftershocks have been felt by people down in Anchorage. And in total, we're up over 11,000. So what those aftershocks, what we can do, aside from just reporting on them, they have some scientific contributions as well. And here we're looking at kind of a cross-section. So we're looking in depth across the Anchorage Bowl area and out into the Matsu Valley. And you can see the main shock is the large circle at the bottom. It's ruptured lower. This entire earthquake happened within the Pacific Plate. I'll talk about that in a minute. And the cloud of earthquakes is one of the ways that we're able to define how much, basically the fault size from this earthquake. Because this earthquake didn't happen at the surface, there's no expression. We don't have any roads that have shifted or fences that have bent. No way to ascertain exactly how big the rupture is. And so looking at the aftershock sequence like this can help us constrain how big of an area actually moved from this earthquake. And you don't just have to wait for aftershocks. There are some fancier mathematical processes that you can do to interpret what the fault looks like simply based on the raw waveform data. And when you superimpose that, you see it actually matches up quite well with the aftershock cloud. So it kind of gives credence. These are 2 data sets derived in 2 completely separate ways, but they match up pretty well, helps us give a pretty good idea of the size of this earthquake, at least in the how much of it actually moved under the earth. When we look at the actual aftershock sequence, so we're going in time here, this is through the end of November of last year, and just a cumulative count, so the number of earthquakes with time, starting at 0 being the start of the main shock. And you notice it follows a pretty distinct shape, that at the start there were a lot of earthquakes in a really short period of time. The first month or so was dominated by a huge number of earthquakes. Then in probably about the 6 months following that, they start to gradually decrease. So the rate of them is dropping down and down and down until you get to where we're currently at now, and that rate starts to be leveling out. And when you look at the magnitudes of these aftershocks, they actually follow a similar pattern as well, to where most of the larger aftershocks happened within the first month or so. And since then, there are still large aftershocks that are felt by people, but they're getting further spaced in time. And in general, the overall magnitude is going down. So as time goes on, what it ultimately means is it's not impossible for a large aftershock to still happen, but the probability, the risk of it happening is decreasing with every day, every week, every month that goes on. So now looking a little bit at what caused this earthquake, what actually happened under the earth. And so most of the seismicity in the state of Alaska is dominated by the Pacific plate, tectonic plate, getting pushed under the North American plate. And so that plate is continually moving every day. It's moving a little bit more. It often can lock at the boundary between the 2 plates. That can cause one type of earthquake. But earthquakes can also happen within the subducting Pacific plate as well. And so the reason for that, what ends up happening is it's much like imagine a stick. That stick would be the plate, and as that plate's getting pulled down by gravity, at some point, if you pull down hard enough for long enough, it'll probably snap. And that's exactly what happened during this earthquake. We call it an intra-slab earthquake. So the earthquake didn't happen at the interface between the 2 plates, but within the single subducting Pacific plate. And so it's like a little fault, a little break within the plate itself. That's not normally how we often, when we describe Earth, when we learn about earthquakes in school or whatever, that's not kind of what you sort of think of the strike slip or the subduction. You don't, or spreading apart. You don't really think about these. They're not really taught. But the fact is, they're not actually that unusual. If we look even in Alaska itself, over the last 100 years, there have been 10 of these interslab earthquakes that have been at least of a magnitude 7.0. And even if you restrict that to just Cook Inlet, there have been 3 magnitude 6 or greater in the last 5 years. So these are actually a fairly common kind of earthquake. And so that alone doesn't necessarily make this earthquake unusual. When we look at the aftershock sequence, we'll compare. So we'll go back. Iniskin was, of course, the earthquake further south in Cook Inlet, but it was felt strongly on the Kenai Peninsula and in Anchorage. When we look at the aftershock sequence, so these are the same sort of things. This is only for 30 days following the earthquake. Both of these earthquakes have the same general shape. The numbers, the amount of aftershocks are different, but they're still following the same pattern of each other. And in fact, it doesn't even need to be these intra-slab earthquakes. That if you look at the offshore Kodiak earthquake, the magnitude 7.9 in January of that year, which was a very different type of earthquake caused by a completely different mechanism, that aftershock sequence follows the same shape as well. And so in the end, you're kind of forced to conclude that there wasn't actually scientifically anything all that unusual about this earthquake. So if it wasn't unusual, why was it so impactful? So after we have a large earthquake like this, or even smaller earthquakes, the question we always get asked, always, what was the magnitude of that earthquake? And I'm going to propose here today that that's not actually the question people care about. That's what they think they want to ask us, but that's not actually what they care about. What they want to know was, how strong was the shaking that I felt? And how long did I feel that shaking for? They're good questions, they're complicated questions, and they're questions we don't often have the answer to when people ask. So in some ways, I'm kind of glad people don't ask us that, because we don't always have the ready answer for that. And the reason for that is that the answer to those 2 questions depends on a lot of things. It depends on the amount of energy that the earthquake released. That's obvious, but that's one of the major contributors, and that's kind of where the magnitude gets back to. But it also depends heavily on how far you are away from that earthquake. It depends on the geology in both the large scale, so the miles around you and the miles below you matter, and the feet around you matter. So even the really shallow geology or the really large scale geology, they both matter. And the engineering, which is to say, if you're in a building, what building are you in? Where in that building are you? They all matter as to and influence how you experience an earthquake. Technically, there's a few other things that matter too. I'm not going to talk about them because they're complicated and don't actually contribute large in the grand scheme of things. But first, we'll talk a little bit about the energy and what that means. And so a warning for any physicists in the room, I'm going to play fast and loose with some stuff here. Please forgive me my sins, but it'll hopefully all be clear at the end. When we talk about energy, if you ask your typical seismologist like me, I would want to say that the earthquake energy, I would give it to you in something called Newton meters, which is a measure of torque, which is a rotational energy that's exerted onto a system. And we happen to use Newton meters. They're a very convenient unit for calculations, but they're not terribly intuitive for somebody to picture. It's defined as the force of a 1 kilogram mass accelerating at 1 meter per second squared applied to the end of an arm 1 meter long. Does that make sense to everybody? Can you picture exactly how much energy is contained in that? Yeah, I actually can't either. But when you use those units, that's often how we report energy of an earthquake. Technically, it's called a seismic moment. When you look at the Anchorage earthquake, that amount of energy was 4.7 times 10 to the 19th Newton meters, which is a huge number. It's inconceivably large. And it's so large that it doesn't really mean a whole lot. So, given that it's pretty hard to visualize, let's pretend that we're more like Hollywood and attempt to quantify this in perhaps a little bit different kind of units. So pounds of TNT, why not? Think of it as you can correlate that at how much explosion energy potential exists within 1 pound of TNT. Funny enough, that's actually a rigorously defined amount. It's defined as 1.9 times 10 to the 6 Newton meters. Okay? So if you do the quick math there, you get the Anchorage earthquake be 25 trillion pounds of TNT. Also an unfathomably large number. And the truth of the matter is I don't routinely play with dynamite in my day job, so I don't really have a good feel for what 1 pound of TNT even is. So one final conversion I'll do that hopefully brings it all home is this is roughly equivalent to the amount of energy used by all of GVA customers in 2018. So it's a lot of energy. But that's not the only factor that goes into how big of you feel shaking. Distance matters. Distance matters greatly. And so for an example, I'm going to pull these 3 Cook Inlet earthquakes. Actually, I'm going to ignore Squentna for now. We'll just look at the Anchorage and the Aniskin earthquake. And these are super convenient to look at because they're the same type of earthquake and they're the same magnitude. So you can assume roughly that the energy released by the two is at least close enough to the same to make some comparisons. And so when we look at the amount of energy that an earthquake releases is fixed. It's like an explosion, a single point in time that it generates its energy and it's done. And then that energy radiates outward over time. But it's the same amount of energy, and as it radiates outwards, that amount of energy is spread over an area that gets larger and larger and larger. And so the further away you get, the less amount of energy is contained within your little point in space. We call that geometric spreading. And so it's roughly equivalent, it's proportional to the energy at a point is something like 1 over distance squared from the source. It's the only equation, I promise. What that roughly means is basically if you're twice as far away from the earthquake as somebody, you only feel 1/4 of the energy that they did. So distance matters hugely. The amount of energy rapidly decays as you get further and further away. So looking at those 2 earthquakes, if you look at it on a map, well, it's obvious, of course, if you were standing in Anchorage, I would expect to feel shaking a whole lot stronger from the Anchorage earthquake than the Aniskin earthquake, simply because I am much closer to it. There is one other important factor in this distance, though, and that's depth. Depth is just as valid of a distance as along a map is. And so when you factor in the fact that Aniskin earthquake was at about 80 miles depth versus the Anchorage earthquake, which is only 30 miles, that contributes too. So even if you're at a point directly above the Aniskin earthquake, it still had to travel 80 miles to get to you. And that bears out when you look at the actual shaking that was measured during these 2 earthquakes. Despite them being the same magnitude, the same earthquake type, the shaking was dramatically stronger for the Anchorage earthquake, especially directly over it. And that is entirely due to that distance factor and the depth in particular. So next, we'll look a little bit about how geology can play a role into this factor. And so here I'm going to show a little animation. This was produced by Professor Carl Tape at UAF. He's a seismologist with the department. This is a simulation, so it's a computer simulation of the Anchorage earthquake. And he modeled it based on the energy, or the earthquake source, and then looking at what the large-scale geology is under the Cook Inlet area. And so as this plays, you see the main shock energy come out here, and you can see that some of the energy gets trapped in these areas, and then they reverberate around and resonate back and forth and back and forth. And that contributes in particular to how long you feel the shaking. The main shock energy has long since passed you, but going on and on. That energy is still trapped within these geologic layers. And so you can feel that shaking even minutes after the main shock ended. Turning to local geology as well, we partner with the USGS and operate a network of stations, seismic stations in Anchorage directly. It was actually the whole network was conceived basically for this kind of earthquake. This is one of the greatest data sets for strong motion data that exists in the country, I think, fair to say. And it helps emphasize some really key points about how local geology impacts it, because you assume in the large scale thing, in the terms of miles, the whole area of Anchorage is roughly, regionally speaking, the same kind of geology. It's about the same distance, give or take, from the earthquake. And so the only reason you can explain strong differences here is the local geology. And what I mean by local geology is, what are you standing on right now? Are you standing on rock? Are you standing on soil? Are you standing on sand at the beach? It all matters, and it influences it really, really strongly. If you were standing here at that circle, the little circle there, you would have experienced the Anchorage earthquake fundamentally differently than if you were standing here. And that's entirely due to what you are standing on right there. The last thing I'm going to talk about here for how the source of magnitudes and energy is engineering, so the building that you're in. This is an animation produced by the USGS from the Atwood building in downtown Anchorage. This is one of the most seismically instrumented buildings in the country. There are sensors on almost every floor of this building and down into the surface below that as well. And so this movie shows the building during the earthquake. It's greatly exaggerated, so don't pay too much attention to the actual movement, but pay attention to the colors in particular as it goes along. So the earthquake coming, and after the initial source of energy, the whole building moves the same. You don't really see anything here, but as the stronger damaging waves start to arrive, you see some resonance set up in the building. And the top in particular starts swinging back and forth and back and forth. And so again, if you were on the ground floor of the Atwood building, this would have been a very different earthquake for you than if you were on the top floor. And even, a minute afterwards, the top floor is still seeing 4 times the amount of shaking that the ground floor was. And this sort of response from the buildings is very common. All buildings exhibit this, and it doesn't even have to be a large earthquake or a particularly tall building to see this kind of effect. About a month ago now, there was a magnitude 3.7 in Esther. Certainly remember this one, mostly because we were in a staff meeting at the time. We felt it, and so our duty person was like, well, I guess I'm done with the meeting, and ran off. But the engineering building, the eLife building on campus, has 7 strong motion instruments in it as well. And you see the same sort of thing. I don't have a fun movie of it, but again, you see the same thing, that on the basement floor, you pretty much see one strong pulse of energy, and that's kind of it. Whereas on the 5th floor, you would see this strong ringing that exists for many seconds longer than the actual signal to the building was. And so this type of experience happens, like I said, for all kinds of buildings and all kinds of earthquakes. So putting it all together, looking at the story of ground motions from this earthquake, each one of the red triangles on here are the acceleration, so our best estimate of shaking that was observed on a seismic site in the ground. And the yellow ones are from people's responses. The USGS runs a thing called the Did You Feel It page, if you've ever logged on to that. This is what the data is actually used for. There's an algorithm that asks you, it asks you a bunch of questions, how you felt the earthquake, and through thousands and thousands of these, they translate them into rough estimates of what the shaking was. It's not perfect, it's not as good as a real sensor in the ground, but it also helps fill in gaps. We can't instrument every point in the entire Earth. That's not possible, but people live a lot of places, so they can help. And so what you end up seeing here is that, so obviously there's no reports, there's nothing within 30 miles, and that makes total sense because it was 30 miles underground. So you can't, there was no way, unless you put a sensor in miles underground, there's no way you could get closer than that. But Anchorage and Eagle River in particular were quite close, Wasilla Palmer a little further away. And then you go out further into mainland Alaska, and you see a pretty standard decay. That's mostly due to our geometric spreading that we talked about. And then a large scatter, even amongst equal distances, and that is due to the geological influence. And so from this earthquake, this sort of quantitative way to see how large that scope, that spread can actually be. It's dramatic. So the next thing to point out that people have asked is, was this the next big one? And while it was immensely impactful, it's not necessarily what people think of when they say the big one, or when they're talking about the big one. So we showed this before, sort of an example of where this earthquake happened, why it happened. When they think of the big one, they usually think of a megathrust earthquake, which is exactly here where the two plates meet each other, they lock, they build up a lot of friction over time and then release all at once. These are the kind of earthquakes that rupture over huge areas, that can generate so very large earthquakes. They can generate tsunamis. This was what the 1964 earthquake was. And so it's fundamentally different tectonically from what the Anchorage earthquake was. And to give a sort of size comparison here, we're looking at a plot. This is all of the seismic energy released in Alaska in 2018. Forgive the fact that it says 7.0. I forgot. There's a few in here that show 7.0. We initially released this earthquake as a 7.0 and then revised it a few months later to 7.1 as we got more data. Doesn't impact anything, but that's why it says 7.0 in places. Regardless, the offshore Kodiak in January of that year dominated the amount of release. It was about 20 times more energy than the Anchorage earthquake was. And all of the Anchorage aftershocks, all of the offshore Kodiak aftershocks, they all in that tiny little gray slice of the all other 2018 earthquakes. So the aftershocks don't contribute to a main shock. They don't matter in the grand scheme of things. They're just a reaction to the readjustment of the Earth to that main shock. And so this alone kind of starts to re-emphasize the fact that, yeah, this one it definitely wasn't the big one, for sure. And if you look at all of the seismic energy released in the United States over the last 50 years, offshore Kodiak shows up. It's a pretty good slice. And that Anchorage earthquake, they're calling it South Central here from ADN, you can barely see that little sliver amongst all of that. Alaska still dominates everything because we have more earthquakes than anywhere else, so of course it adds up, but the slice gets even smaller. And then when we compare it to the 1964 earthquake, then it gets really crazy. That entire circle would represent, the previous showed was the yellow circle for Alaska, basically. And so the Good Friday earthquake just dominates over that. It was the largest by far, and it doesn't even matter, yeah. And a lot of that is based on, we look at the rupture patch. So this is the amount of area that actually moved during the earthquake. And if you look at the Anchorage earthquake, it ends up being about a 10-mile in the long direction rupture patch. If we zoom out, and we'll look at what the 1964 rupture patch was. There you go. Goes from Prince William Sound past Kodiak, a total rupture distance of a little over 500 miles. You can't even see the Anchorage one anymore. So this was not the big one. It could be a whole lot worse. That being said, it was dramatically impactful for the people there. And so we can't stop earthquakes from happening. We can't predict earthquakes. So what might the future hold? What can we do to help alleviate some of the risk from large earthquakes in the state? One potential is something called earthquake early warning. The first thing I want to point out is earthquake early warning is not earthquake prediction. It doesn't say there's going to be a magnitude X earthquake within the next 2 weeks. That's not what it's about. What it is, though, is the ability to alert people in the matter of seconds to maybe a minute before the strong shaking arrives. And so you could rightfully say, okay, that's only a few seconds. What good can that actually do me? I can't secure my house. I can't do a whole lot with it. But a lot can be done if you give somebody 30 seconds advance warning. The utility companies can shut down things that could cause major problems, fires, danger to people. They can terminate those and have them all safe. You can slow down trains so that they don't derail. You can abort aircraft takeoff and landings at the airport. If you're at a hospital, you can tell the surgeons to stop. And for you, it gives you time to get somewhere safe. If you're in a room like this, it gives you enough time to find somewhere safe, hop under a chair, a desk, whatever, maybe get out of the building before the earthquake happens. Because most likely, direct result from an earthquake is you're going to get hurt from things falling on top of you. So anything you can do, any advanced time, because once the shaking starts, it's almost impossible to move. You're kind of stuck where you are, so the best you can do is duck and cover. So if given advance warning, you can do something about that. So little basics of how earthquake early warning works. It relies on a physics principle of earthquakes, that there's two kinds of waves that get generated by an earthquake. One's called a P wave, which is the yellow line there. These travel fast. They're the fastest waves. They tend to not do damage. They're just sort of, if you felt a stronger earthquake, especially one that's kind of close by, you might notice first a bump, and then a couple seconds later, the strong shaking. That bump was the P wave. And then the strong shaking that arrives later is the S wave. And so the S waves, they fundamentally travel slower than a P wave, which is really great because given the right sensors, if you put enough sensors in close to the epicenter, the location of where that earthquake starts, you can use those sensors to detect those P waves and attempt to rapidly assess how big that earthquake was before it hits a population center. This, of course, relies on the fact that the earthquake is far enough away from the population center to make a difference. For Anchorage, that probably wouldn't have helped much, but that's not always the case. You can get really advanced with kind of earthquake early warning. This is a screenshot from a system that's deployed on the West Coast in California now and is being rolled out to Oregon and Washington this year. It goes a little above and beyond. It attempts to give you a countdown time of how long before that shaking hits, an estimated intensity. It'll try to estimate, and the magnitude is kind of how it derives all of that. And it will send out alerts to people within the areas that are expected to experience strong shaking through things like your cell phones, through the emergency systems on TVs, radios, things like that. However they can, they'll saturate anything that's available to try and alert people with enough time to do something about it. This is a plot that was produced, or figures that were produced by the USGS a while ago when they were developing this system. Take these numbers with a huge grain of salt. There's a lot of assumptions in here that aren't really based in reality. But in a perfect world, a system could, for instance, from the 1964 earthquake, could have given Anchorage 30 seconds of warning. The Denali Fault earthquake could have given Fairbanks 30 seconds of warning. The Aniskin earthquake was closer to a minute because it was further away. So this kind of system does have good potential for alerting people, but it's not the only way. This is a really advanced, this is a really expensive system, complicated technically to pull off. They're still struggling in California. I can't even imagine what it would take logistically to pull off here. That being said, it doesn't have to be so advanced and complicated. If you go to Amazon, you can find some silly quake alarm. This is technically early warning. I have no idea if this thing works or not, but it relies on the same principle. It relies on the fact that a P wave travels faster than an S wave, and so I think this thing is supposed to detect the P wave and give you a few seconds of warning before the S wave hits. But I don't know. That price tag is a lot better than what the shake alert system in California is costing, though, I gotta say. So, a few take-home points from here, things that we kind of learned from the Anchorage earthquake. First one, it doesn't take the big one to cause damage and potential loss of life. We got lucky for the loss of life. This size of an earthquake, this close to a population center, we were expecting to hear of casualties. There were a lot of close calls. If you talk in the schools and things like that, it wouldn't have taken much for some serious problems to hit. That being said, there still were many millions of dollars of damage caused to public property and private property. A lot of homeowners have serious damage to their houses and don't know how to pay for it. This is still impacting people 2 years later, and it will for years to come. Location matters more than anything else. If you're really close to an earthquake, you're gonna feel it really strong, and any potential for pre-alerting for it just goes out the window. There's not much we can do about that. We can't pick up and move Anchorage away from a seismic hazard zone, unfortunately. So instead of that, preparedness matters. There's lots of good resources out there for how to prepare prior to an earthquake. We have some on our website. The federal government has documentation, has info for you. The state government has lots of stuff. We've got handouts up here as well if you're interested. That matters more than anything else. And knowing how to stay safe during an earthquake. Be like those kids. There are role models for how to react when an earthquake hits. They knew exactly what to do, and if those ceiling tiles would have started to fall, they probably would have been fine. And lastly, don't underestimate the psychological impact. We often, me excluded necessarily probably, but we like to think of ourselves as the rugged Alaskans. We're capable of handling anything. We can put up with anything we want. But an earthquake is a traumatic experience. There are lots of people who are experiencing post-traumatic stress symptoms from this earthquake. The aftershocks trigger responses in people. We're all human in the end, and you can't anticipate how you're going to react to a highly stressful situation like that. So always keep that in mind. Not just you, but kids, family, pets, they all get influenced by this. It's a life-altering experience for them. That's what I have. Thank you very much.